Hi everyone, welcome to the brand new section, Deep Learning for Time Series Forecasting. In this section we'll explore three various types of neural networks for time series forecasting for two models. For each of the model we start with multi-layer perceptrons, MLP. This will be followed by recurrent neural networks which include long short-term memory, LSTM, and gated recurrent units, GRU. Finally, we'll cover convolutional neural networks, which are mostly used on images. Now we move on to the first video of this section that deals with air pressure time series forecasting. In this video we'll use different neural network architectures, such as MLP, RNN and CNN, to extract complex patterns from the data and develop time series forecasting models. First, let's start with MLP. Multi-layer perceptrons, MLP, are the most basic forms of neural networks. An MLP consists of three components: an input layer, a bunch of hidden layers, and an output layer. The dataset used for these examples is on air pollution measured by concentration of particulate matter, PM, of diameter less than or equal to 2.5 micrometers. A couple of time series models have been developed, one on air pressure and the other on PM 2.5. The dataset has been downloaded from the UCI machine learning repository. We can visit this web link for a problem description and downloaded datasets. So, let's start by importing these packages required to run the code. Then we'll execute this line of code to set the working directory. After setting the current working directory, the dataset is read from the .csv file to pandas dataframe. Let's print the shape of the dataframe. On executing, we can view the shape of the dataframe, as in our case it's 43,824 rows, along with 13 columns. Using the head function, we'll print the first few rows of the data frame. Now, to make sure that the rows are in the right order of date and time observations, a new column, datetime, is created from the date and time related column with this block of code. The new column consists of Python's datetime.datetime object. The data frame is sorted in ascending order over this column. Let's execute it. The press column has the data on air pressure. Let's draw a box plot to visualize the central tendency and dispersion of press. Here, the box plot of air pressure shows that there are no observations that can be designated as outliers. Presence of outliers can be used to decide the loss function for training the neural network. Next, we plot the time series of air pressure for the entire duration of the observations. Let's execute this block of code. As you can see here, the generated plot displays the time series of air pressure for the entire duration of the observations. Gradient descent algorithms perform better, for example converge faster, if the variables are within range -1,1. Many sources relax the boundary to even -3,3. The press variable is min-max, scaled to bound the transformed variable within 0,1. Min-max scaling of a variable x is done with this equation. This formula would result in x underscored scaled epsilon 0,1. After that, include these lines of code. Here, this variable scaled underscore pres is used for developing the time series forecasting model. For making prediction on the original variable pres, we apply suitable inverse transformation on the model's prediction. Before training the model, the dataset is split into two parts, train set and validation set. The neural network is trained on the train set. The validation set is used to evaluate the model and to determine the number of epochs of training. All the steps involved in model training and validation is done by calling appropriate functions of the Keras API. Let's start by splitting the data into train and validation sets. The dataset's time period is from Jan 1st, 2010 to December 31st, 2014. The first 4 years, 2010 to 2013, is used as train, and 2014 is kept for validation. Executing this block of code to implement the splitting of data. It will also print the shape of the train and validation sets. Here we can see the shape of the train and validation sets. So first, we'll print the first few lines of train data frame. Later on, print the first few lines of validation data frame. With this line of code, we'll reset the indices of the validation set. Now let's plot the train time series of scaled underscore pres using this code snippet. You can see the generated time series of min-max scaled air pressure in trained dataset. After that, we'll generate another time series of scaled air pressure in validation set using this code snippet. Time series of min-max scaled air pressure in validation dataset. Now we need to generate regressors, x, and target variable y for train and validation. A 2D array of regressors and 1D array of target is created from the original 1D array of the scaled _ pres column in the data frames. So, by adding and executing this block of code, we define a function that takes the original time series and the number of time steps as input to return the arrays of x and y. Next, we'll run this couple of lines to print the shape of the train array. Here, the makeXY function is called to generate the train set. On executing, you can view the values of shape of train arrays. Also, we'll execute these lines of code to calculate and print the shape of validation set. Here, the makeXY function is called to generate the validation sets. The output of the print function is displayed as shown on the screen. Further, we'll define the MLP using the Keras functional API. This block of code will import the required Keras package. In this approach, layers are declared and cascaded as input and output of each other. Add this line of code to declare the input layer with shape none, 7 and of type float32. Here, the none indicates the number of instances that's determined at runtime. Then we'll execute this code snippet where the dense layers are declared with linear activation. Dropout has been used to regularize deep neural networks. In this example, a dropout layer is added before the output layer. Dropout randomly sets p fraction of input neurons to 0 before passing to the next layer. Randomly dropping inputs essentially acts as bootstrap aggregating or bagging type of model ensembling. Random forest uses bagging by building trees on random subsets of input features. In this line of code, we use p is equal to 0.2 to drop out 20% of randomly selected input features. Finally, the output layer gives prediction for the next day's air pressure with this line of code. The input, dense and output layers will now be packed inside a model, which is the wrapper class to train, and make predictions. Mean square error, MSE, is used as the loss function. So let's add these lines of code. Here, the learning rate of a weight is updated based on exponentially weighted moving averages of the weights gradients and the squared gradients. On executing the code, the summary function displays layer-wise details, such as the shape of input and output, and number of trainable weights. The model is trained by calling the fit function on the model object and passing the x_train and y_train. A model checkpoint object tracks the loss function on the validation set and saves the model for the epoch at which the loss function has been minimum. So let's execute this block of code. On executing it, you can see that the output is getting generated. It will take a couple of minutes to complete the execution. Once the code is completely executed, the output will display train on 35057 samples and validation on 8753 samples. Predictions are made from the best saved model. The model's predictions, which are on the standardized air pressure, are inversely transformed to get predictions on the original air pressure. With this highlighted part of the code, we'll calculate the goodness of fit, or R². Post that, we need to import R² score package from scikit-learn metrics library. After importing the package, we'll execute this couple of lines to calculate the R² for the validation set and display its value. As an output, you can see the R² of the model on the validation set is 0.9921. Lastly, the first 50 actual and predicted values of air pressure are plotted using this code snippet. Let's execute it. The generated plot is displayed on the screen where you can see the actual and MLP-predicted time series of air pressure. Further, let's talk about recurrent neural networks. RNNs are notoriously difficult to be trained. Vanilla RNNs, the kind of RNNs that suffer from vanishing and exploding gradients that give erratic results during training. As a result, RNNs have difficulty in learning long-range dependencies. For time series forecasting, going too many steps back in the past would be problematic. To address this problem, long short-term memory, LSTM, and gated recurrent unit, GRU, which are special types of RNNs, have to be introduced. Let's start with executing actual and LSTM-predicted time series of air pressure. We'll continue to use the dataset on air pollution to demonstrate recurrent neural networks for time series forecasting. Executing and pre-processing the data remains the same as we've done for the examples on MLPs. We just need to include a few additional code statements to plot the LSTM time series of air pressure. To add an LSTM layer to the neural network, we first need to import the LSTM class from Keras. Then we'll calculate and print the shape of the 3D arrays. Previously, we had calculated the shape of 2D arrays. Here we'll calculate and print the shape of 3D arrays with these lines of code. Here, the makeXY function is used to generate arrays of regressors and targets. Those are x_train, x_val, y_train, and y_val. x_train and x_val, as generated by the makeXY function, are 2D arrays of shape which includes number of samples and number of time steps. However, the input to RNN layers must be of shape that includes number of samples, number of time steps, and number of features per time step. In this case, we're dealing with only PM 2.5, hence number of features per time step is 1. Number of time steps is 7, and number of samples is the same as the number of samples in x_train and x_val, which are reshaped into 3D arrays. On executing the code, you can see that the x_train and x_val have been reshaped to 3D arrays, and their new shapes are seen as an output. Further in this couple of lines of code, we've implemented the neural network to develop the time series forecasting model as an input layer, which feeds into the LSTM layer. The LSTM layer has 7 time steps. Only the last time step of the LSTM returns an output. There are 64 hidden neurons in each time step of the LSTM layer. Hence, the output from the LSTM has 64 features. Next, the LSTM's output is passed to a dropout layer that randomly drops 20% of the input before passing to the output layer, which has a single hidden neuron with a linear activation function. So we'll implement this by executing these lines of code. Finally, with this code snippet, all the layers are wrapped in a Keras model's model and trained for 20 epochs to minimize MSE using the Adam optimizer. Executing it, we also print the summary of the model. In this output, we can view the summary which displays layer type and output shape along with the summary. Now, we'll add and execute this block of code. Here the model is trained by calling the fit function on the model object and passing the x-train and y-train. The training is done for a predefined number of epochs. The validation dataset is also passed to evaluate the model after every epoch completes. A model checkpoint object tracks the loss function on the validation set and saves the model for the epoch at which the loss function has been minimum. On executing it, you'll see that the output is getting generated. It will take a couple of minutes to complete the execution. Once the code is completely executed, the output will display train on 35057 samples and validation on 8753 samples. After we've achieved the output, we need to add this block of code. Here the predictions are made for the air pressure from the best saved model. The model's predictions, which are on the scaled air pressure, are inverse transformed to get predictions on original air pressure. And with this part of the code, we set the working directory and provide the file name which is created on executing the previous code. Let's execute the code. Post that, we need to execute these lines of code, where in the first line of code we import the R2 score package from scikit-learn metrics library. Then, in the next line, we execute the goodness of fit. R² is also calculated for the predictions on the original variable. With the last line, we print the message and display the value of R². On executing this code snippet, we can see the output as R² on validation set of the original air pressure as 0.9837. Let's plot the first 50 actual and predicted values of air pressure with this code snippet. So here we can see the output of first 50 actual and LSTM predicted time series of air pressure. Next, we'll be plotting GRU-predicted time series of air pressure. So, we'll start by importing the GRU class from Keras with this line of code. After importing the class, we'll add this block of code to calculate and print the shape of 3D arrays. The input to RNN layers must be of shape. That is, number of samples, number of time steps, number of features per time step. Here, number of features per time step is 1, number of time steps is 7, and number of samples is the same as the number of samples in x_train and x_val, which are reshaped to 3D arrays. As an output, we can see the generated value for the shape of 3D arrays. Post that, we define input layer, which has a shape of none, 7, and of type float32. None indicates the number of instances. Along with that, we also have added GRU_layer, which defines 7 time steps. Then we'll add dropout layer and output layer. The GRU's output is passed to a dropout layer that randomly drops 20% of the input before passing to the output layer, which is a single hidden neuron with a linear activation function. Finally, the output layer gives prediction for the next day's air pressure. Finally, all the layers are wrapped in a keras.models.model, trained for 20 epochs to minimize MSE using the Adam optimizer. We'll also print the summary of the TS model. In the generated table, we can see the output of GRU_1 layer, along with the output shape as none, 64, and param value as 12672. Next, we add and execute this code snippet. Here the model is trained by calling the fit function on the model object and passing the x_train and y_train. The training is done for a predefined number of epochs. The validation dataset is also passed to evaluate the model after every epoch completes. A model checkpoint object tracks the loss function on the validation set and saves the model for the epoch at which the loss function has been minimum. In this part of the code, we need to specify the data file's location. In our case, we've saved the files in the datasets folder. This is the data file which is present in the datasets folder. On executing it, you'll see that the output is getting generated. It will take a couple of minutes to complete the execution. Once the code is completely executed, the output will display train on 35057 samples and validation on 8753 samples. As prediction are made for the air pressure from the best saved model, the model's predictions, which are on the min-max scaled air pressure, are inverse transformed to get predictions on original air pressure. So we'll implement the predictions for air pressure using best model. Post that, we need to execute these lines of code. Where in the first line of code we import the R2 score package from scikit-learn metrics library. Then in the next line we execute the goodness of fit. R² is also calculated for the predictions on the original variable. With the last line we print the message and display the value of R². On executing this code snippet, we can see the output as R² on validation set of the original air pressure as 0.9954. Let's plot the first 50 actual and predicted values of air pressure with this block of code. On executing the code, we'll see the output for the actual and GRU-predicted time series of air pressure. Lastly, we'll see air pressure time series forecasting by 1D convolution. We'll continue to use the air pressure dataset to demonstrate 1D convolution for time series forecasting. To develop a convolutional neural network, we need to import these 3 classes. Then we'll add this block of code to reshape the arrays. Post reshaping, we'll also print the shape of the arrays. The input to convolution layers must be of shape, that is, number of samples, number of time steps, and number of features per time step. Here you can see the output. So, in this case we're modelling only press, hence number of features per time step is 1. Number of time steps is 7, and number of samples is the same as the number of samples in x_train and x_val, which are reshaped to 3D arrays. Now we define the input layer, which has shape none, 7, and of type float32. None indicates the number of instances. With this line of code, we add a 0 padding 1D layer after the input layer to add zeros at the beginning and end of each series. 0 padding ensures that the convolution layer does not reduce the dimension of the output sequences. Pooling layer, added after the convolution layer, is used to downsample the input. Next, we add a conv1D layer. The first argument of conv1D is the number of filters, which determines the number of features in the output. The second argument indicates the length of the 1D convolution window. The third argument is strides and represents the number of places to shift the convolution window. Lastly, setting use_bias as true adds a bias value during the computation of an output feature. Here, the 1D convolution can be thought of as generating local AR models over a rolling window of 3 time units. Also, execute this line of code. After that, we add a line of code to define average pooling layer. Average pooling 1D is added next to downsample the input by taking average over 3 time steps with stride of 1 time step. The average pooling in this case can be thought of as taking moving averages over a rolling window of 3 time units. We've used average pooling instead of max pooling to generate the moving averages. The previous pooling layer returns a 3D output. Hence, before passing to the output layer, a flatten layer is added. So let's add it with this block of code. The flatten layer reshapes the input to number of samples, number of time steps into number of features per time step, which is then fed to the output layer after passing through the dropout layer. Finally, all the layers are wrapped in a keras.models.model and trained for 20 epochs to minimize MSE using the Adam optimizer. The layers are packed into a keras models.model wrapper and trained to minimize MAE using the Adam optimizer. We'll also print the summary of the TS model. Next, we add and execute this code snippet. Here, the model is trained by calling the fit function on the model object and passing the x_train and y_train. The training is done for a predefined number of epochs. The validation dataset is also trained to evaluate the model after each epoch completes. A model checkpoint object tracks the loss function on the validation set and saves the model for the epoch at which the loss function has been minimum. In this part of the code, we need to specify the data file's location. In our case, we've saved the files in the datasets folder. This is the data file which is present in the datasets folder. As predictions are made for the pres from the best saved model, the model's predictions, which are on the standardized pres, are inverse transformed to get the predictions of original pres. So, we'll implement the predictions of air pressure using best model with this block of code. Post that, we need to execute these lines of code, where in the first line of code we import the R2 score package from scikit-learn metrics library. Then in the next line we execute the goodness of fit. R² is also calculated for the predictions on the original variable. With the last line, we print the message and display the value of R². On executing this code snippet, we can see the output as R² on validation set of original air pressure has 0.9951. Let's plot the first 50 actual and predicted values of pres using this code snippet. On executing the code, we'll see the output for the actual and pres predicted time series of air pressure. In this video, we've plotted air pressure time series forecasting with MLPs, LSTM, GRU, and 1D convolution.